let's learn about real-world applications of quadratics. Before we go into actually doing some word problems, I want to show you what in algebra we usually think of as these quadratics and how they apply in math class, and then we're going to take that and apply it to how that looks in the real world in a lot of different situations. So the first thing I want you to look at is an x and a y-axis. I haven't labeled it yet, but you all are normally accustomed to labeling this as the x-axis and the vertical as the y-axis. And in a t-chart, that looks like x and y because that's how we write the ordered pairs. Let's look at this in terms of a function. In function terms, the x is your input, what you plug into it, your independent variable. Your y is typically your output. Or that thing that you get out. On a t-chart, input goes with the x and output goes with the y value. In function notation, a lot of times this looks like x and f of x. So again, that would look like x and f of x, meaning you plug x into the f function. What does this look like in most of the real world applications? Typically, you're dealing with time and some form of distance or height. Time is usually the input or the x value. You can't change time. Time is not dependent on anything. Time just keeps going. So time is usually the x or the input. And the output, well, that depends on what you're dealing with. Distance, height. I'm going to use height for our example. So again, in your t-chart, that looks like time is the input and height is the output. So then let's draw a picture and see what this looks like as far as the parabolas we've been graphing. We're going to go ahead and pretend like there's somebody down here who has thrown a ball, maybe. We've already practiced labeling our parts of the parabola. This is your vertex, right? And we've labeled that as an ordered pair x and y. But in this example, x is time and y is height. Well, how did we get those values when we were calculating that to graph it from a standard form? We used opposite b over 2a to get the time or the x or the input, and f of opposite b over 2a to get the height or the output. So that's how all of those are related, lined up together. So when we put in opposite b over 2a, that gives us the x value of our vertex. That tells us how far over to go. So opposite b over 2a, and that's why that's your x value at your maximum or your minimum height. And then when you plug that back in, that gives you the actual height at that time. Let's look at our roots right here. At this point on the graph, how high am I? I'm at ground level. I'm at 0. It's called a 0. if some problem is asking you how long, so I'm solving for time, how long does it take for the ball, or fill in the blank, to hit the ground? If it's hitting the ground, it means it's got a height equal to 0. Well, then you just want to find your roots right here. You know how to find your roots. So this would be, in real world terms, the landing time. And we would solve that by either factoring and set those equal to 0, or quadratic formula. So there's your overview of the applications that we're about to look at. So let's look at this first example. The average height in centimeters of a certain type of grain can be modeled by the function h of r equals blah blah blah, where r is the distance in centimeters between the rows in which the grain is planted. Based on this model, what is the minimum average height of the grain, and what is the row spacing that results in this height? That sounds really hard. It's not that bad. I don't even understand what I just read until I go back and read it again, sometimes a couple of times. Let's, at this point, just look at how our function was named. H of r. H of r. That means r is my input, h is on the outside, it's the output. Again, r is on the inside, it's the input. H is on the outside, it's the output. When y'all are thinking of your x and y t-chart, in this case, it's gonna be r is on the x-axis and h of r is on the y-axis, input, output. So if it helps you to go ahead and draw a picture of that, then do that. All we've done is look at the name of the function. This is r, and this is h. What do those mean? H is the average height. So h is height. What's my r? Let's go back and look and see, what does r mean? R is the distance between rows. They give you a quadratic function. You know how to graph those. Those are some funky numbers, but you know how to graph that. Based on this model, what's the minimum average height? That's the question. Minimum average height. And the row spacing that results in this height. Okay, well, I don't know for sure the exact location of all this, but I do know that it's a positive lead coefficient, so my parabola is going to open up. It's going to look something like this. We know for sure that the y-intercept is 33.6, and it's asking us for a minimum. A minimum happens at the vertex. You know how to find a vertex of a quadratic. So let's take everything we know algebraically about quadratics and apply them to real stuff. To find your axis, which is the x value of your vertex, in this case it's the row distance, opposite b over 2a. Opposite b would be a positive 1.28 over 2 times a, 0.024. When
when you do that calculation, you should get 26.7, and these are measured in centimeters. Okay, what does opposite b over 2a go with again? Remember your T-chart. X, Y, input, output. In this case, row distance, height. To get the X value, it was opposite b over 2a. And to get the output, it was f of opposite b over 2a. So we currently have this value. Now we need to plug that back in. H of 26.7. So 0.024 times 26.7 squared minus 1.28 times 26.7 plus 33.6, and then you're going to do the math on that. When you calculate it, you should get 16.53 centimeters. So we found this vertex to be at 26.7 and 16.53. And again, this is in terms of row distance and height of the plant. So the minimum average height would be 16.5 centimeters if we plant the rows 26.7 centimeters apart. How about mileage? The highway mileage, M, in miles per gallon for a compact car is approximately M of S equals, where S is the speed in miles per hour. What is the maximum mileage for this compact car to the nearest tenth of a mile per gallon, and what speed results in this mileage? So let's just label our function. I have M of S. S is my input. M is my output. So instead of X and Y, instead of input and output, I have S and M. Let's label that on a graph. My input is the x-axis, that's S. My output is M on the y-axis. Let's label those things. M is miles per gallon. S is speed in miles per hour. And you're given a quadratic with a negative lead coefficient, so it's upside down. That is not to scale. It's asking you maximum mileage. Maximum is at a vertex. We know how to do a vertex. We find a vertex by opposite b over 2a, which is your x value of your vertex, and f of opposite b over 2a, which is your y value of your vertex. In this case, that's going to correlate with our speed at the maximum, and this is going to correlate to our miles per gallon. So we just have to calculate those things. opposite b over 2a be a negative 2.45 over 2 times our a value of negative 0.025. A negative and a negative will make a positive. And when you calculate that, it rounds to about 49. Again, that is our speed, because that's our axis or our x value. So x, which x here is speed. So that's miles per hour. At 49 miles per hour, we maximize our gas usage. How much gas am I using at that point when I'm maxing it out? So I'm going to do m of 49. Do those calculations. So your vertex is at 49 miles per hour, maximizing your gas mileage at 30 miles per gallon. Example 3. You're trying to dunk a basketball. You need to jump 2.5 feet in the air in order for you to be able to dunk that ball. The height your feet are above the ground is given by that function h of t equals negative 16t squared plus 12t. What is the maximum height your feet will be above the ground? And does that mean will you be able to dunk the ball? So let's draw our picture. Input is t. That's gonna be time. H is output. That's gonna be height. It's an upside down parallel because it's a negative 16t squared. Your feet are on the ground here. You jump and then you land. Maximum. Maximum is at a vertex. Opposite b over 2a, plug it back in. It's the same process over and over again. Will you be able to dunk the basketball? Okay, so we need to find that vertex. For this, I only see 2 terms. It's ax squared plus bx plus c as a standard form. So my a value is negative 16 and my b value is 12. My c value is 0. That makes sense because my y-intercept is at 0. Okay, so my x-axis in this case is time, would be opposite b, so negative 12 over 2 times a, negative 16. Negative 12 over negative 32. A negative and a negative make a positive, and put that in your calculator. Gonna get a decimal. I left mine in fraction form, but feel free to compare my fraction of 3 over 8 with your decimal. That's the time. The question is, how high do my feet go? So now I need to do f of x, or plug it back in. So h of 3/8. Again, feel free to use your decimal here if you want to. Negative 16 times 3 over 8 squared plus 12 times 3 over 8.
2.25 feet. You're going to be able to jump, your feet will be 2.25 feet off the ground. It wants to know, can I dunk the basketball? Well, if I need to jump 2.5 feet to reach the rim, and I only jump 2.25 foot, then no. Ms. Darden cannot dunk the basketball. One more example. This is the majority of the types of problems that you're going to see as it relates to application. A basketball is shot with an initial velocity of 24 feet per second from 6 feet above the ground. Use the position function. H of t equals negative 16t squared plus v naught t. It's kind of like not, like N-O-T, but not. It means the origin, the beginning, plus h naught. V naught is the initial velocity, and h naught is the initial height. This position function is so applicable in real world situations. When you get to calculus, you can work backwards and discover where this comes from. It actually comes from speed and acceleration due to gravity. It's wonderful. We're going to use it in our quadratics application. You need to know this. With this problem, let's just plug in what we know. The initial velocity is 24 feet per second, and the initial height is 6 feet above the ground. So h of t equals negative 16, there we go, t squared, plus the velocity 24 times t, plus the initial height of 6. And there is your quadratic function for this ball being thrown. So if I throw a basketball and it leaves my hands at 6 feet, there you go. That's how that works. Write an equation to model the path of the basketball. I just did that. That models it. How high does the ball go? How long does it take to get to that height? How long does it take for it to hit the ground? At what time will it reach 7 feet? All these questions. Let's try to answer them. Let's just draw our picture and label it the way we've been labeling it. The input is time. The output is height. It says that we start at 6 feet. So that person is 6 feet tall. And they throw the ball and then it lands over here. How high does the ball go? Maximum height is a vertex. We know how to find a vertex. We find the x value for the axis, which in this case is time, by opposite b over 2a. All day, every day. Opposite b would be negative 24 over 2 times a, which is negative 16. So negative 24 over negative 32, a negative and a negative equal a positive. Put that in your calculator. You get 3/4 of a second, or 0.75 seconds. That's not what it was asking me on that one. It does ask me that for C, doesn't it? How long does it take to get to the maximum height? We just figured that out. 0.75 seconds. But I still want to know how high the ball goes. Well, so we got to plug it back in, because height is an output, so we have to plug it in. So h of 0.75. Negative 16 times 0.75 squared plus 24 times 0.75 plus 6 should yield 15 feet. So the ball goes 15 feet.
how long does it take the ball to hit the ground? The ball hits the ground here. That's a root. We find roots by either factoring or using quadratic formula. So you're gonna have to use quadratic formula to find how long it takes to hit the ground. Unless that thing will factor. Opposite B. Plus and minus the square root of B squared minus 4 times A times C all over 2A. When you plug that into your calculator and do your calculations, you're going to get a negative value, that would be back here, and a positive value. Does it make sense to use the negative answer for time? No. We can't travel backwards in time. We don't have a time machine. So we're only going to use the positive solution, which is 1.72 seconds. I think that's right. Make sure you can get that. At what time does the ball reach 7 feet? Okay, let's make some sense out of this. At what time? I'm solving for t. Does the ball reach 7 feet? It says, what time? That's the question. When the height is 7 feet. So use the equation that you have, negative 16 t squared plus 24t plus 6. When does this t give me an output or a height of 7 feet? If it releases at 6 feet, it's going to hit 7 on the way up and it's going to hit 7 on the way down. So in this case, we're actually going to use both of our solutions as long as they're both positive. But you know that we can't solve this quadratic unless everything has been moved over. So now that we've set up the equation, let's solve it. Subtract 7 from both sides and you get negative 16 t squared plus 24t minus 1 equals 0. Use A, B, and C in your quadratic formula. And do the quadratic formula again. So the setup for that would be negative 24 plus and minus the square root of 24 squared minus 4 times A times C all over 2 times A. Calculate your quadratic formula for that, and you should get 0.04 and 1.46 seconds. Both of those times. Because if you release it at 6 feet, it's going to hit 7 feet here and here. That time would be 0.04 seconds and 1.46 seconds. Last question. If the rim of the basketball hoop is 10 feet, is it possible for this ball to make it into the hoop? If the rim is 10 and we said it could go 15 feet, then yes, it is possible, depending on where you shoot it from, for that ball to be able to make it into the hoop. And those are all the examples for quadratic application.